Welcome everybody to the second part of lecture number 4, where we're gonna start by discussing a special case of wire dipole antenna, which is the famous lambda by 2 dipole. So the lambda by 2 dipole, in terms of like analysis, it's the same thing as arbitrary length dipole antenna. The current distribution would lead us to find E theta and H phi of this format. So we just go back to the first part where we did the analysis. Just gonna bring, so we did the analysis here for arbitrary length, and here for lambda by 2, this 2 pi over lambda multiplied by lambda by 2 will give us cosine pi over 2, which is 0, and we are left up with this expression for the radiated field, both E theta and H phi, and this is similar to all the other dipole antenna where the other component in R and direction is 0, as well as E phi and H theta. So in order to complete the analysis, we need to calculate the radiated power. So the average power density is proportional to the square of the fields, and there is a famous approximation that we're going to talk about shortly for this function here, which is this between bracket term is approximately equal sine theta to the power 3. And from the radiation density, we can get the radiation intensity U by just like multiplying by R square. So we have this expression here for the intensity. The total radiated power is integrating this average or power density. Average here is average over time, one period. So integrating this quantity with respect to the whole parameters. Here the only dependency is on theta, because the dependency on phi is uniform, as we know, and the remaining integration is on theta. And this term, like, we can do it numerically, and also does have some closed form expression with some approximation, but this is the total radiated power from a lambda by 2 dipole antenna. Once we have the total radiated power, we can calculate directivity, which is U maximum over average or like isotropic power intensity, which is B radiated divided by the total 3D angle 4 by strident. So this is D naught, and its value for lambda by 2 antennas 1.64. The effective aperture is lambda square over 4 pi multiplied by directivity, which is 0.13 lambda square. The radiation resistance equal the radiated power divided by I naught square, which give us around 73. So the input impedance for the lambda by 2 dipole antenna does have this expression here, Z input equals about 73 ohm real part, and it does have imaginary part. Many times, in order to achieve like matching, we need to eliminate the reactive part of the impedance, and this can be achieved by shortening the lambda by 2 antenna roughly like 0.03 or 0.02 lambda, depending on the wire radius. And as we're gonna see, this will like take the reactive part of the input impedance to 0. The radiation pattern is this like H shape, or the sine cubed of theta dependency. This is for the power, and we can see that the intensity can be approximated to the to sine cubed of theta, and there is other approximation like sine to the power 2.8 or sine to the power 2.6. 2.6 is the closest. As we're going to see here, we can approximate the black one here. This H-shaped black one is the exact, and we have 3 different approximations: sine cubed, sine to the power 2.8, sine to the power 2.6, and we can see that the sine to the power 2.6 is the closest, but the 3 approximations are acceptable from engineering perspective. Now we're going to talk about another topic. This topic that had been discussed before in static electric field, which is the image theory, to solve the problem when we have an electric source on top of a perfect or good conducting large plane. So the idea here that we did before, like we used the image theory in electrostatic to solve many problems, and today we're gonna do the same and study the use of image problem, or sorry, the image theory or image method to solve a problem of an antenna, like wire dipole antenna existing on top of a ground plane, a conductor ground plane, or a perfect conductor ground plane. Why this is important? Because for many different frequencies, the earth or ground acts as a good conductor, so we need to deal with this situation. Okay, so this is the setup. If we have like a vertical electric dipole on top of a perfect conducting plane, if this is the original source or the actual source will like send or like radiate electromagnetic waves to the observation point. Also, the radiation from this vertical dipole will hit on the conducting plane. This is a perfect conductor plane, to just formulate the problem, and then part of this reflected wave will reach to the observation point. So this is called multipath, and it's a major issue for analysis in wireless communication and in radar and many different applications. So for each observation point, there is actually 2 components of the radiated field that reach the observation point: the direct one, and the other one is the reflected. When we study like this problem, we can use the same technique that we used for electrostatic field, is that we can put an imaginary source, and this is where the name image theory came from. We can put an imaginary source at the same height as the original or the actual source in the bottom plane, and you will find that we can express the reflected wave as it is coming from this imaginary source. So we can say and prove that the radiation at any observation point is composed of 2 components: the direct component and the reflected component. The reflected component can be implemented or presented as coming from an imaginary source at the same height from the perfect conductor boundary in the other direction, and we'll talk about the polarity of this source. So here it is the same polarity, as we're gonna see. So now we can just remove this conductor and deal with the problem as like uniformly filled with air or this dielectric material with one actual source, one imaginary source, and we can find the field exists in the upper half plane because of this setup. The field that we're going to find in the lower half plane is meaningless, so it doesn't mean anything. It just exists as like a collateral effect of the formulation. But the field in the upper half plane in the equivalent problem of actual source and the imaginary source is the same as the radiated field caused by the actual source and the reflected components from this perfect conductor. So like we're saying, the problem is equivalent. If we remove this conductor and put imaginary source, the boundary condition would be satisfied. The field distribution or the source distribution is satisfied in the upper half plane. So the solution of the original problem with the conductor existing and the equivalent problem of actual source and imaginary source placed in a way to fulfill the boundary condition is bringing the same field in the upper half plane. So to fulfill the boundary condition, if we have an electric dipole, an electric source that is oriented in the vertical direction, the image would be the same polarity. So if the current is flowing in that direction in the actual source, the image would have the current also flowing in the same direction. If the source is horizontal, so it's a horizontal source, its image would be same height, same distance from the interface, and it is in the opposite direction. Why is that? That is the setup that fulfills the boundary condition of zero tangential electric field at the boundary of perfect conductor. For the magnetic source, if we have a magnetic current, equivalent magnetic current on a perfect conductor, the vertical magnetic dipole would be solved by like inverse polarity vertical magnetic dipole. The horizontal magnetic dipole would be associated with horizontal magnetic dipole in the same direction. If the dipole is inclined like this one, the image would be this one. Why? This is the setup that fulfill the boundary condition of zero tangential electric field at the interface of the perfect conductor. If we have a perfect magnetic conductor which is conducting a magnetic material, ferromagnetic material with very high permeability, the situation would be like similar. Vertical electric would be associated with opposite vertical electric, so on and so forth. So the reflection or image theory. Now we come to the formulation. How would we solve or analyze this problem of a dipole on top of a perfect conducting plane? So as I said, like we're gonna just remove the conductor. Here it's a perfect conductor, and substitute its effect by an imaginary source located in the opposite direction of the actual source at same distance. So if we have infinitesimally short dipole on top of a ground or perfect conducting plane, the field that the radiation field that reach the observation point is a direct component and a reflected component. The reflected component can be presented by this imaginary source, as we just said. So here the vector from source to observation for the actual element is R1 with angle theta 1, and the two vectors from image to the observation point is R2 and theta 2. From the origin it would be theta and R. So this is the actual setup, and we have a very famous approximation when the distance R is much larger than h. So the observation point is far enough, or like very far from the source region. So E theta, because of the direct link, is the expression here. We have like infinitesimally short dipole. The E theta, because of the reflected wave, is RV. This is the reflection coefficient, and it is theta 2 and R2. In case of perfect conductor, RV will equal 1, and the total radiated field is the direct radiated field and the reflected radiated field. This is from infinitesimally dipole element of the antenna. So if R is much larger than h, then we can do this approximation. We can approximate the three vectors from actual source to observation, from imaginary source to observation, from origin to observation, to be parallel, so the same theta, and of course they still have different lengths, R1, R, and R2. So if we just write down the expression for R1, we'll find that from the cosine angle law, it would have R square plus h square minus 2RH cosine theta, which is the angle between the source to observation vector and the position vector of where theta is the angle between the position vector of the source and the position vector of the observation point. And here the famous approximation, we can neglect h square with respect to R square because R is much larger than h, and you can use Taylor series expansion. Taylor series expansion would give us that R1 for the actual source equal R multiplied by 1 minus h over R cosine theta. With similar approximation, we can find R2, which will equal R plus, multiplied by 1, or like R plus h cosine theta. So this is the approximation. For the phase term, we're going to use the more accurate expression, R1 equal R minus h cosine, R2 equal R plus h cosine. We said that the approximations, the three thetas are the same. The three vectors are parallel because the distance is much larger than the height. And for the amplitude term, because the amplitude term is not that sensitive, we approximated all the distances to be equal. So doing that would have, like, this is a common factor, and then when we add the direct and reflected, would have this expression, and as we're going to see next lecture, this is called the array factor. So we can say the total field equals the field radiated from a single element multiplied by the array factor. And one important thing here, for z less than 0 in the, like, below the perfect conductor, actually there is no radiated field, even though it would get an expression from the image theory, because in the image theory we removed the perfect conductor. This finding in the lower half plane is meaningless. So if we have like an arbitrary length antenna, in like the real antenna is a arbitrary length of length equal L. We're going to integrate the radiated field over the whole length of the antenna. So dE theta, what we found in the previous slide, is the radiation from an element, infinitesimal current dipole antenna, and we integrate over the whole length. So we find that it will equal this expression. Here, of course, if we have like a length, we'll have a current distribution, and we integrate over the length. So this is the element factor again, and this is the space factor. And we will end up with the element factor multiplied by the space factor, as we're gonna see in the antenna array lecture next week, inshallah. So when we have this, if the antenna is directly, so here this sketch is something like new, because we have phi symmetry we just presented on theta, and because theta in this direction and that direction is the same, and we know that it will be an 8 shape, like number 8 is the shape. So here we have a dipole antenna with h equals 0. That would give us this pattern. If we are to draw the whole pattern, we'll have another arc like this on the other side. When h, the distance, is lambda over 8, it's this curve. Again, if we want to draw it completely, we'll draw the other similar half on the right hand quarter. And if h equal lambda by 4, it would be this one, so on so forth. So if h equals 3 lambda over 8, it would be this pattern. If we want to draw the complete pattern, we'll just copy this on the left quarter, so on so forth. And here, just pay attention, there is no field in the lower half space. So the field exists only on the upper half space from theta equals 0 to theta equal 90. There is no field here because of the ground plane is causing shielding. So if we have like an antenna and we just go like at a higher height from the perfect conducting plane, we'll have so many loops. So if h equal 2 lambda, we'll have so many loops. If h equal 5 lambda, we have like that many loops, and some people calculated the number of loops and they come up with this approximate expression. So in order to study the situation, we would go directly to calculating B radiation, and the radiation would be E square multiplied by ds over a half sphere. Why? Because there is no radiation in the lower half space. So phi is integrated from 0 to 2 pi, but theta is only from 0 to pi over 2. So the radiated field would have this expression here, and the power intensity, just multiplying this by r square. So we have this expression for the power intensity. Again, the power radiation is over just half sphere because there is no radiation in the lower half space. Just giving the expressions and calculating the power intensity. The directivity would have this expression here, and the radiation resistance would have this expression, which is 2b radiation over I naught square. Just repeating the expressions. So the maximum directivity is achieved when we are about 0.46 lambda above ground plane, and the directivity is 8.1 dB. So like see like the very high effect of the ground plane on the directivity, because it's sort of like two elements instead of one. And this is the pattern for the maximum directivity case. And this is the curve that's showing the directivity, radiation resistance as a function of height. The radiation resistance is on the left, the directivity is, the radiation resistance on the right, directivity on the left. And this is for very short dipole, infinitesimal dipole. So monopoles and dipoles are used widely in wireless communication. For example, like for the walkie-talkie, we have a monoball, like on cars, the old cars, we have like a monoball. Like many cases, we have like a monoball attached on top of a metallic plane, and this is like very common practice. So when we have like a monoball attached to like a perfect conductor, actually from the image theory, it's as if we have a dipole in free space, because this arm, the image for this arm would be another source here. So if this is lambda by 4, this is very common, the whole effect would be as a lambda by 2 antenna, lambda by 4 monopole and another lambda by 4 image, and we get a lambda by 2 antenna this way. For monoball, Z input is half that of the dipole. The directivity of a monoball is double the directivity of dipole, because the power radiated from monoball is half the power radiated from dipole, but it is focused in just one half space. For lambda by 4 monoball, it's half the input impedance of lambda by 2 dipole. And here we have like a quick note about the difference between R input and R radiation. We discussed this before. In general, they are not equal to one another, because in many cases IN doesn't equal I naught. But as we showed before, at lower or like short length up to like lambda by 2 dipole antenna, they are very close, because the maximum and maximum or I naught and I at the input are the same, so they are very close to one another at short dipoles. So here I'm announcing homework in a week from the discussion session, assignment number 1, which is due in like 2 weeks from the discussion sessions. Now we need to just discuss a couple of issues that is related to the existence of wire antennas or antennas in general on top of ground plane. So like there is a number of definitions that are important. So this angle is called the grazing angle, which is the angle from the line of horizon, and the incident angle is the angle that we are dealing with, the angle from normal to the surface. So there is two definitions here. And when we have the earth as the ground plane, the earth is very large, and if the earth is very large compared to the used wavelength, the earth here I mean the radius of the earth, or the radius of curvature of the earth in this area is very large compared to the wavelength, and the grazing angle is greater than 3 degrees, it is a very good approximation to approximate the ground plane effect as a perfect like a flat surface. So this is a good engineering approximation. And in terms of conductivity of the ground, it depends on the components of the soil, if it's like seawater or like fresh water, or if it's land or agricultural land or whatever it is. There is differences, and many times we are doing something like that. We put like a net of wires, conducting wires, on the ground so that we enhance the performance of the ground as a perfect conductor, to promote, like, if the conductivity is limited, when we do this we can like make it closer to perfect conductor. And also, like, we need to consider the polarization and the reflection for different polarization of the field also is considered. The curved surface of Earth does have an effect, and there is this effect is handled by introducing what's called the divergence factor, which is reflected field from curved surface over reflected field from flat surface. They are different. So here, if this is like a source, and you like reflect this source on top of a flat surface, would have certain pattern here that can be drawn. But if the surface is curved, it will cause some redistribution of the energy in a different way, and this is handled as an approximation again by the divergence factor, which is area contained in a circle by area contained in an ellipse for radiation from curved surface over radiation from flat surface. So in general, the effect of Earth on radiation pattern is that the Earth is not a perfect conductor, so we need to take the limited conductivity into consideration. The Earth is not flat. Another factor is that the Earth is not smooth surface, and smooth or not, like curved or not, or like flat or not, depends on the wavelength. If the wavelength is a short wavelength, we can just consider it flat, and if it's a very large wavelength, we can consider it smooth. So like for short wave, the roughness shows up. For large wavelength layers or like long waves, the flatness need to be considered. In all cases, the conductivity effect need to be taken into consideration. Thanks everybody for watching the video, and meet you in the discussion session. Assalamu alaikum.